I'm going to be talking about like a much more applied approach than what you heard before for one specific problem with, I think, a graph network that most of people here should be familiar with in some way. So the context for the problem is structures, solid materials, where we create materials, where we design bridges and other structures, and we want to be able to understand why they behave under certain loads. And I'm going to argue that for a lot of these materials, we need a multi-scale approach, where we heard about the multi-scale graphs before. This is like the multi-scale materials. I want to talk about like a different concept, where if we have, for example, a wind turbine blade of the size of 100 meters, the properties of that blade are, in principle, depend on the smaller scale properties, right? So depending on the orientation of fibers in a fiber reinforced polymer, that influences how the macro scale wind turbine will fail, for example. And so we don't just want to understand how it behaves, but we're designing these as well, right? So ideally we can want to change or optimize properties at the lower scale to influence like the most efficient design at the macro scale as well. And so we just heard a bunch of talk already about like solving PDEs. And so one way to do it is using the finite element method, right? Where we have a number of boundary conditions and we try to solve for an equilibrium in a domain. And for our case specifically, we often have a sort of non-linear material model. So depending on if you have concrete or steel, your material will behave differently. And so to find equilibrium, we need to, at our integration points of our finite element method, solve a non-linear problem as well. And for a lot of materials that we use, like most buildings are built with this method and it works quite well, we can define this quite accurately. But for some materials, like I said earlier, this really depends a lot on these micro scale properties. And so then we can use a different, okay, one step back, we can use the single scale method to solve this on the domain and see, for example, a solution where in the middle we have sort of strain localizing. This looks like it's dynamical. It is not dynamics. Everything in my talk is going to be about like static simulations. But so to get a more accurate simulation, we need to go to what we call a multi-scale approach, where in every integration point of your finite element method, we embed another finite element method to get the properties from. So here we have two different materials at the lower scale, which we can define very well on their own. But again, combined, it really depends on the orientation of the fibers or the layout, what the actual response will be. And so solving a single scale is still quite fast, but doing this for every integration point solve another system becomes really, really expensive. And that's why people turn to a machine learning approach, where we try to replace this part using some kind of surrogate model. And so the general method that people use is we create a bunch of data trained on these individual microscale simulations, train a neural network based on that is then used to, from the strains, predict the stresses as an output. Now, when we have a material that, for example, damages, the history of the material is quite important as well. So a very common approach is something like a recurrent neural network for this. And this works decently well. It is much faster to evaluate than this full microscopic model. And it allows us to still simulate these materials. However, there's some properties that we lose by doing this approach, right? Well, first of all, everything becomes an approximation, like we have no guarantee that we are correct. But on top of that, we no longer have this like really multi-scale approach, right? If we want to change the orientation of the fibers, there's no way to do this by default because we only take the strains as input. We need to train a new neural network, for example. Also, what I'm personally quite interested in my PhD is after our surrogate becomes sort of uncertain about what it needs to do, we want to be able to sort of switch back to our finite element method that can then sort of take over for part of the domain. We keep the machine learning method in 90%, but for example, 10%, we go back to using the finite element method. But to get that, we need sort of the history of all the paths for this sort of full field simulation. And with a recurrent neural network, we don't get this information. So that's why we motivated to use a graph neural network that doesn't just give the average output, but predicts this full field microscale as the output. And why a graph neural network? Because we're using with meshes, it's like a very natural way to deal with it. And so to be able to switch back, we basically don't just want to get the average quantity out, but we want to get the full field quantity at this lower scale for both the stresses and the strains. And so I want to talk a little bit about design choices you can make, because in the finite element method, we apply boundary conditions on the nodes, for example. Then we have the material model in the integration points of each element. But for this multi-scale approach, we only have as an input this macroscopic strain, right? And so we again choose, what we talked about before, a dual graph, where we replace each element with a node. And that way, like all the information of our graph network itself lives in this space that we actually care about, this for the strains and the stresses. Like I said before, we don't have like a sort of dynamical simulation. So like normally if you like pull on one side, everything needs to change like immediately, right, over the whole domain. And so this brings some challenges to how you design the GNN, which is a bit different from, I think, the sort of typical GNN that more spreads information around the graph. And so to still capture this without needing, as many message passing steps as you need elements, we chose to give the macroscopic strain directly as an input feature to every single node. And so with that, each node already knows what the sort of overall structure behavior should be, and it's more like a local updating on what it should be then. Another thing that we gave then is sort of the location of each element relative to like the local geometrical information. So in this case, we have voids. This could be some other information that learns how close am I to this, that influences how it will perform in the end. And so I want to talk a little bit about, I've talked about the inputs, giving this full strain already. And for the outputs, we know that we want to get these three quantities, and we could use the GNN to just predict all of them at the same time. But we already have a relationship for how to go from the strains to the stresses. This is this relationship that we also use in the normal finite element simulation for the micro model. And so we can just use this to directly go from our strains to stresses. And from the stresses, we can just average them basically to get our output. So we can sort of separate the machine learning part and the physics part. But we find that it is quite important to still include both of these terms in our loss function. So we still train through our material model, right? So this is a sort of non-linear problem that we also need to solve using like a Newton-Raphson solver that is included inside our differentiation of the learning process. The architecture looks like a big mess, but it follows a sort of standard encoder process decode, like the mesh graph nets architecture. And what we added is this material model, right? That is the main part that we sort of added to this. The rest is a bunch of mostly trial and error, I would say, and a lot of parameters. So with this, I hope this works. Yep. What I'm plotting on the left is the predicted and the true strains. And then we can use, like I said, this material model to go from our strains to our stresses. And here you can see that even though the stresses are fully dependent on the strains, this is a non-linear problem, right? So we get a very different patterns between these. And that's why we need to include both the strains and the stresses in our loss function. Then we can, this is the equivalent basic strain, so that is sort of determines the history. I think I skipped over that a bit. Oops. That is like the sort of internal variable that accounts for what it has seen in the past already. And then finally, we can sort of average these quantities to get the output that the finite element simulation needs or uses in the end for the macro scale simulation. So we added this material model and we wanted to say, what is the influence of adding this, right? If we completely remove it, for example, and just use the GNN to predict the outputs directly, or we only use it in training, but then turn it off again, or turn it on after training, or what if we remove some connection that actually speeds up training quite a bit? What is the influence of those things? And we see, I think, mainly looking at this bottom table, that using the material model during like the training process and inside this backpropagation scheme does add quite a bit of performance to the model and does make it better as well. Then we use this trained GNN on like small microstructures to go to like a much larger microstructure. And we have this sort of loading and unloading pattern in this case. And if you like look at this plot long enough, you will see that there are some differences. But for us, this is still like quite good that we can extrapolate. I'm never sure where you're extrapolating with GNNs, but we were still quite happy with how this performed. Then, as a slide, I talked about we want to speed up these finite element simulations, right? And here I want to show that we do indeed make it faster than using the finite element method. Even though it's still like quite expensive, I think if you use a recurrent network, it would basically be 0 all the time. It is quite a bit more expensive than that, but it scales much, much better compared to the finite element method when we keep this, or as we scale up the problem to having more elements. And what I show here is still a very, very small problem compared to what we need in practice. So I think I spoke very quickly, but my conclusions basically are that we have implemented this graph neural network for multi-scale simulations. And I've talked a bit about like how we, what kind of design choices we made to make it work for our specific application. I think there's still a bunch of improvements that could be made. For example, we broke a bunch of symmetry rules, it's no longer equivariant, those kind of things that I think are important to use it in practice. But we focused on the material model itself for now. If you want to learn more, you can scan this link, and yeah, thank you for your attention.